that this is my favorite periodic table. So whichever atom you go to, it lists here, then it gives you the details of the atom, which is really good. There's only two places that I really go to. I go to this one, and the other one is Wikipedia. Wikipedia does an incredible job on atoms. But that's really what I wanted to show you, where I'm going to get stuff. So we are starting chapter 5. We talked about the exam details. So note that I didn't post this up online because that's all I had for what we started talking about. We just outlined exam 2 and that's it. So what I want to say, so I'm going to start chapter 5 right now. So let's go and do that. So to really kind of start off and sort of like the way of thinking about what is going on, I want to propose a little thought experiment. And I think it's an important thought experiment because it really sets up the idea of what I'm trying to get across here. So the first thing that I want to do here is that I want to say that suppose what we're going to do here is that we're going to take large rocks and then we're going to hit it with a hammer, a sledgehammer. So suppose we start with a large rock and use a hammer, a sledgehammer, to break it down into smaller and smaller pieces. So if you think about this process here, I start off with the rock that's large, and then what do? I hit it, and as I hit it, I create smaller rocks. And then as I continue along this process, we could then say, okay, so now I got small rocks. Now I have small stones. And then if I keep hitting this, the small stones turn into pebbles. And if you keep hitting the pebbles, maybe now it turns into gravel. And if I keep hitting the gravel, I then get to sand. And I think you got the idea now of where I'm trying to go. The question is, as I get smaller and smaller and smaller, dot, 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 do things continue to get smaller indefinitely or forever? Can I continue this process and get, just get smaller and smaller and smaller? And the answer, according to physics, is no, you cannot do this. Physics claims that there is a limit to how small objects can get. And so what I want to do here is to give you a sense of what do I mean by this process. I want to look at a video. And this video is an old video. It's called Powers of 10. By the way, there are much better ones of what I'm showing you, but this is really about the order of magnitude in size. And the way they look at them is that they look at them in factors of 10. So let me go share this video with you so you could see what I'm talking about. So here's this video, the powers of 10 video. Okay, so what you're doing here is that you're 10 million light years away from the Milky Way. So you're outside the Milky Way. And then what you're doing here is that you're getting smaller and smaller, and they're going to focus on Earth. So here we go. So they're going to update the image every 1.5 seconds. So here we go. Let's start this now. So now you're in the Milky Way. Now they're looking for the solar system. Now they're going to focus on Earth. And this is where we really are starting to look at this thing. So now you're looking at the surface of a leaf. And what you're seeing in these dark lines here is you're actually seeing mountain ranges and valleys at the microscopic level. So if I continue to move, you could see that as you get smaller and smaller, you get more and more detail. So you get a series of valleys and mountain ranges at this level here. So we are going from cells to now chains of molecules. And now we're looking at a molecule. And a molecule is a collection of atoms. And then you get to one of these atoms, and this is what they call the electron cloud. And you're in this cloud, and now you're between the electrons and the nuclei. And this is considered a microcosm. And there's a reason why they call that. We'll get to that later. And now we're focusing onto the nuclei. And I think that's it. That's the extent of where it goes to. So if I was to kind of try to summarize this process here, I need to go to my OneNote, make sure that I'm in the right spot. What we sort of like kind of started to look at here is that if I was to sort of like scale this stuff, I imagine that I have a collection of atoms. Okay, so let's say that this is my collection of atoms. And these atoms are what we call, this collection of atoms is what we call molecules, or this could be a collection of molecules, which are then cells here. So again, maybe I should have written that this is a collection of molecules. And maybe I should have just said that this is a cell. And then what we find here is that as I continue to go smaller, then I focus on a single molecule, right? In this case, I'm now having a single molecule. And so when I look at this single molecule, what you find here is that this guy is really a collection of atoms, like H2O. That's a single molecule, but it has 3 atoms. So if we continue to go smaller, then we get to a single atom. So here we get to a single atom. And when I look at this single atom, what we're going to see here is that I get a nucleus. So that's going to be my nucleus here. And the image that most people have of atoms is that the electrons are going around in a circle here. And so what I'm seeing here is that I have these little electrons sort of like really sort of like whizzing along here. And I would say that, yep, that's what people say are the electrons. And then this is what people say is the nucleus of the atom. So let's talk about this single atom. And what I would say here is that this image of an atom is called the Rutherford model of the atom. And this Rutherford model of the atom a lot of times goes by the word planetary model of the atom. So it's a planetary model. So when I look at this, what I'm really saying here is that I have a solar nucleus, and the solar nucleus has little tiny electron planets that whirl around us. So Rutherford discovered the nucleus in 1911 or 1910. And put forth this planetary model. Rutherford knew immediately that this model was a bad model, right? He knew that this was a model that does not work. But yet, that model still continues to this date. And what we find here is that this is a very common image of the atom. This is called the Rutherford model here. And just to be nice and clear, this is what I want to get rid of. That image of an atom is a bad model. One of the goals in this chapter here is to give you a much better model, which is the quantum mechanical model of the atom. And there's very, very strong data that shows that why this is a bad model. But that's where I'm really going with this. So now, here we go. So what we want to do here is that atoms, what we know here is that atoms are the building blocks, and for all intensive purposes, they're the building blocks of all. No. What I said was absolutely wrong. Atoms are the building blocks of almost all observable matter. So a lot of times people will say that atoms are the building blocks of everything. That is not true. And I'll clarify what I mean. So just to stick to where I want to head here, observable is a very important word right here. And I'll have to define what do I mean by observable. But the question is, what is an atom? And you're going to see that we're going to do this over 3 chapters. So when I think about an atom, I see that there's 2 parts. There's the electrons. This is what we primarily deal with in this chapter. So this is sort of like the physics of electrons is really chemistry. Chemistry takes us, and maximizes the effect of these guys. So chemistry only deals with electrons. And that's the subject of chapter 5. But when I look at the atoms, there's also the nucleus. And when you look at the nucleus, this is the realm of nuclear physics. And when we look at that, that's really chapters 6 and 7, where we start to look at that thing.